This video is about the squeeze theorem. We're in the context of calculus working with limits, and so we've seen already some definitions, graphical examples, limit laws. Now we're applying this specific theorem. For our notes, we'll first state the theorem. The squeeze theorem, sometimes it's called the sandwich theorem. You'll see why in a second. It actually is a very fitting name for it. If g of x is some function that is stuck between or equal to some function below it, f of x, and some function above it, h of x, when x is near a, except possibly at a, and the limit of f of x, this lower or equal to function, is equal to the limit of h of x, this higher or equal to function, which is equal to some value L, then think about this. If the outer functions are each approaching some value, call it L, and the function in the middle is kind of sandwiched or squeezed between those two, then we conclude that its value must also approach L. That's kind of the logic behind this theorem. Let's try an example where we want to prove that the limit as x approaches 0 of x squared times the sine of 1 over x equals 0. To prove something means we're already expecting it to be true, but we want to be able to state with clear evidence and theorems and logic that it is true for sure. Now, first of all, let's just kind of recall that given the limit laws we already know, we could say that the limit as x approaches 0 of x squared times the sine of 1 over x equals, okay, so think back to a previous video where we did limit laws. Isn't this a product of functions here? This is x squared times the sine of 1 over x, right? Well, one of our limit laws would state that you could actually take the limit of each of those functions separately and then multiply those limits together. So we have the limit as x approaches 0 of x squared, that was the first factor in the product, times the limit as x approaches 0 of sine of 1 over x, that's the second factor in the product. And you may say, well, let's just do this, because the first factor in this product, the limit as x approaches 0 of x squared, if you go back to our limit laws, this is a case where you can just plug in the value x is approaching to this function. We had a law like this, so we could say, oh, that's just x squared, or 0 squared in this case, and then we'd multiply that by the second factor. Here's where the problem occurs, though. We now are trying to take the limit as x approaches 0 of the sine of 1 over x. But if I tried to plug 0 in for x here, first of all, that doesn't even exist, 1 over 0. And so notice this is not like x is approaching 0 from one side of it, it's just approaching 0. And so if you take a look at the graph of 1 over x, the limit does actually not exist there. So we would have to say does not exist. The problem is 0 times does not exist doesn't give us a very clear result on this. So here's how we can use the squeeze theorem for this particular limit. First of all, let's recall some basic facts about some trigonometry here with sine. Isn't it true that the sine function, and we'll even use the sine of 1 over x since that's what our problem has, but isn't it true that sine of really any input has to be stuck between or equal to -1 and +1? If you think back to the sine function, right, it's just a wave that goes up and down, and it's true for the domain is all real numbers, and it goes no higher than 1, no lower than -1. So that's the basic property of the sine function. And then of course if you put 1 over x in it, okay, so x is approaching 0 here, but the point is it doesn't matter because the domain of sine is any real number. So put whatever you want in for x, 1 over it is still within the domain of sine, which means you're still stuck between -1 and +1. Okay, so that's true and good to know. Let's also recall that with an inequality like we have now here, you can multiply an inequality all the way through by a positive number or a positive value, and it will not change the inequality symbols. Now, if you multiply by something negative, of course it would flip them. But if, let's say, we take this inequality where the left boundary was -1, but now let's multiply that by an x squared. Okay, and then we're going to go all the way through like this. I'm going to multiply the middle expression, which was our sine of 1 over x, by x squared as well. And then even on the right side, we'll multiply x squared by the 1 we had over there. Okay, so now realize that we're multiplying by x squared all the way through, but x squared is guaranteed to be positive no matter what x is, which means we don't need to change, this does not affect the inequality symbols. We can leave this as is. Now, if we go back to our limit laws in a previous video and just review some of them, you will find that, so let's just say here, limit laws, recall those or review those. You'll find that the limit as x approaches 0 of this left part of our inequality here, so negative x squared, okay, that would be a case where you could do actually a couple different laws with this. You could take the negative sign and throw it out in front. You could substitute the 0 in for x. We have two laws that would involve those steps. The point is that value would actually be the same as the limit as x approaches 0 of this right side boundary, which is just x squared, and both of those limits would be 0. Again, just substituting 0, the value x is approaching, into those functions. Now, if the outsides of this inequality are both approaching 0, as we've stated, then what the squeeze theorem states above is that what's in the middle must also be stuck or squeezed in and approach the same value. Well, that's exactly the limit we want to evaluate. So we could say, therefore, 3 dots means therefore, the limit as x approaches 0 of x squared times the sine of 1 over x, right, that is this middle function we had in our inequality, and it happens to be the problem that we wanted to prove above. We could say that that must also equal 0 by the squeeze theorem.